Welcome back to AP Chemistry with Mrs. Mays. Today we're looking at the types of acids in acid-base equilibrium. First of all, there's the monoprotic acid. That simply means that it has only one acidic hydrogen, one hydrogen that pulls away. A polyprotic acid, of course, has more than one, because poly means many. And then we have the oxyacids. An oxyacid means there's the proton attached to the oxygen of a polyatomic ion, like nitrate or chlorate or one of those. Finally, there are organic acids. In an organic acid, the hydrogen is at the end of the carboxyl group, so it's still attached to an oxygen. The carboxyl group is a functional group of organic chemicals, so it's that hydrogen that pulls away that makes the carboxylic acids acidic. These are generally very weak because they don't dissociate completely in water. Polyprotic acids can give us a little bit of heartburn because there's two types of Kas, or more if there's more than two hydrogens. So the first Ka, Ka1, describes the dissociation of the first hydrogen to come away, but then the conjugate base can also lose a hydrogen, and so that's what goes into the second. That's what goes into the second dissociation constant, when the conjugate base also loses a hydrogen, and it leaves the polyatomic ion and a hydrogen ion in the solution to make it acidic. Usually, the Ka2 is smaller than Ka1 because it's always easier to remove the first proton from a polyatomic acid. The structure of the acid will have a lot to do with its acidic properties as well. Any molecule that has a hydrogen in it is a potential acid, but they don't all behave acidically, because the stronger the bond is with that hydrogen, the less acidic that will be. So we would compare bond dissociation and energies to see how strong is that bond. Likewise, the more polar the bond, the more acidic it will be, because this whatever anion the hydrogen is bonded to will be hogging the electrons, and the hydrogen is not going to stick around for that. It's not going to get to share the electrons very effectively. In particular, with an oxyacid, the more polar the anion is that's bound to the oxygen, the stronger the acid will be. Generally speaking, the more oxygens there are hooked to the central atom, the more acidic the hydrogen is. So if we were to compare perchlorate to chlorate and chlorite and hypochlorite, we would see a trend. Remember, the hydrogen is attached to the oxygen atom. So the more oxygen atoms there are bonded to the chlorine, the more the electrons get pulled away from the hydrogen. And those oxygens are electronegative, more electronegative than anything else except for fluorine. So as the electrons get pulled away from the hydrogen, that hydrogen tends to leave and dissociate into the water. So if we just looked at hypochloric acid, then we would see the electron density is highest on the chlorine and oxygen end and lowest on the hydrogen end. But let's add another oxygen here. Now we've got something that's electronegative, pulling those electrons away from the hydrogen. So we increase the electron density on the oxygen side of the molecule. The same is true when we add another oxygen to make chloric acid. The three oxygens now increase the electron density away from the hydrogen. And finally, we have perchloric acid, and that's the most electron dense on the opposite end of the molecule from the hydrogen. So this hydrogen will be most acidic because it's the easiest to get away. The electrons are all hiding out over on the other side of the molecule with the oxygens. Hydrated metals can act on the water as well. They would be pulling on these lone pairs of the water molecule because the metal has such a high charge, then it's going to have a large attractive force for those lone pair electrons. So the water gets pulled towards that ion, and that makes it easier for these hydrogens over here to come off. Non-metal oxides, we just looked at metals, non-metal oxides dissolved in water can make acids. The most notorious of these are the ones from environmental science, the NOx and the SOx. The nitrogen oxides and the sulfur oxides tend to make things that are not good for the environment. So here's sulfur trioxide gas. When it goes into the atmosphere and combines with water there, it forms sulfuric acid, which is the same stuff as the battery acid in your car. So imagine if that was raining down from the sky in acid rain. Ionic oxides dissolve in water to produce bases. And by ionic oxides, we tend to mean metal oxides, like the group 1 and group 2 metals especially. So this calcium oxide in water will make calcium hydroxide, and that's a strong base. Lewis acids and bases form complex ions. So that Lewis acid, water would be the Lewis base in this case, because it's an electron paired donor. It would have a strong attraction for a highly charged metal like aluminum or any other sort of transition metal. So that's why we can surround that aluminum with ligands of water molecules or other Lewis bases like ammonia or chloride, and form a complex ion where the whole entire thing is carrying a charge. So these Lewis acids and Lewis bases have everything to do with electrons rather than having to do with protons. And those are the types of acids that we're going to be dealing with in acid-base equilibrium. So get ready to describe strength of acids using Ka and strengths of bases using Kb. See you in class.